Chapter 15, Section 1, Exercise 6. Before doing Exercise 6, we will review some definitions and theorems. A scalar valued function is a function whose output is a scalar. In our case, a scalar is a real number. A vector valued function is a function whose output is a vector. We will see typically two-dimensional vector outputs and three-dimensional vector outputs. Another name for a function whose output is a vector is a vector field. So again, a vector field is a function whose output is a vector. On the top of page 3, we have the following definition. A vector field, capital F, is called conservative if there exists a differentiable scalar valued function, lowercase f, such that the gradient of lowercase f equals the vector field f. If such a function lowercase f is found, whose gradient is capital F, the vector field, then lowercase f is called the potential function for capital F. The following theorem is a test for a conservative vector field in the plane. Suppose this is our vector field. An input is an element of R2 and the output is a two-dimensional vector. If the partial of n with respect to x equals the partial of m with respect to y, then capital F is conservative. That means there exists a potential function for capital F. And it usually takes integration to find it. We will do that in exercise 6. For a function whose input is an element of R3 and whose output is a three-dimensional vector, we can define the curl of this vector field. This is the matrix definition. Some people memorize this formula, which is simply the determinant of that matrix. This theorem is a test for a conservative vector field in space, in other words in 3 dimensions. If the curl of f is the 0 vector, then capital F is conservative. That is, if the partial of p with respect to y is equal to the partial of n with respect to z, and this other pair of partial equations, if all 3 are true, then capital F is conservative. We arrive at exercise 6. Partial of p with respect to y is equal to 2y times 3x times z squared. In other words, 6xy z squared. The partial of n with respect to z, 3z squared times 2xy, or 6xy z squared. So the partial of p with respect to y does equal the partial of n with respect to z. The partial of p with respect to x, 3 times y squared z squared, and the partial of m with respect to z, the derivative of z cubed with respect to z is 3z squared, and then times that y squared. So we see that the partial of p with respect to x is equal to the partial of m with respect to z. And likewise, it's easy to check that the partial of n with respect to x is 2yz cubed, and that matches the partial of m with respect to y. So these 3 last sets of computations say capital F is conservative. That is, capital F equals the gradient of lowercase f for some potential function it's called. But how do we find this lowercase f? We do this by integration. I don't have a whole lot of space here, so I'm going to have to erase. The gradient of f is fxi plus fyj plus fzk. Those would have to match. Those would have to match, and those would have to match if, and since in this case, the gradient of lowercase f equals capital F. So we integrate partial of f with respect to x. This gives us xy squared z cubed plus some function of y and z. Because if we were to take the derivative of this with respect to x, because it only involves y and z, it would be 0. If we integrate the partial of f with respect to y, we would get 2x y squared over 2 z cubed, or x y squared z cubed, plus some function of x and z would be possible. If we integrate partial of f with respect to z, we would have to match p. We get 3x y squared z cubed over 3 equals, again, x y squared z cubed plus some function of y and z. we see that these match, and the only way to reconcile all three of these statements simultaneously is by a single constant k. And what I mean by that is the only way to have a function of y and z, and a function of x and z, and a function of y and z, sorry, that should be xy. The only way to reconcile all of these is if each of these three is only a constant. So f of xyz equals xy squared z cubed plus some constant k. This is the potential function for capital F.